In this part, we learn how to estimate the term structure from a given set of market quotes on instruments including coupon bonds, LIBOR, forward rates, and swap rates. We will distinguish between exact methods and smoothing methods. Exact methods will give us discount curves that exactly reproduce the market data. But this comes at the cost of somewhat irregular forward curves. If we insist on regular forward curves, we use a smoothing method, which gives us smooth yield curves, but at the cost of not exactly matching the market data. We will eventually see what PCA, principal component analysis, tells us about the basic shapes of the yield curve. We now start with the bootstrapping method, which is an exact method. It is a very simple method and it is most used among trading desks. The idea is to build up the term structure from shorter maturities to longer maturities. And it is most instructive to learn about the bootstrapping method from an example. We look at these following data from the US market on October 1st, 2012. We are given LIBOR rates, futures rates, and swap rates. The day count convention is actual by 360. The aim is to find the discount curve for all the reset cash flow dates that exactly matches these quotes. Let's look at the first block of market data, the LIBOR rates. They're given for overnight, 1 month, and 3 month maturity. We denote these maturity dates by S1, S2, and S3. In terms of the day count convention, the year fractions are given here. The corresponding zero coupon bond prices are given in this one-to-one relation. The next block contains quotes on futures prices. Recall that the futures price for a maturity date TI plus 1 is quoted as 100 times 1 minus the futures rate, which is the futures rate for the period with reset date TI and maturity date TI plus 1. We have 5 futures prices. The reset date for the first futures is T1, is the 19th of December 2012. We use futures rates as proxies for forward rates, as shown here. When looking at the maturity spectrum, notice that we have a maturity overlap, as shown here. The first reset date of the first futures contract lies between S2 and S3, the maturities of the LIBOR rates. From this, we get the LIBOR rate for T1 by linearly interpolating the S2 LIBOR and the S3 LIBOR rates. From the T1 LIBOR rate, we then get the T1 bond, and then we derive the T2 bond using this formula which relates forward rates to ratios of zero coupon bonds. By iterative usage of this formula, we eventually get the T3, T4, T5, and T6 zero coupon bond price. The third block contains swap rates for 9 different lengths. These swaps pay annual coupons at the following 30 dates. The dates marked in red are the dates on which the 9 swaps mature. For these 9 dates, we are given swap rates. What we will do next is we will use linear interpolation to get swap rates for the black dates U6, U8, U9, and so on and so forth. We will get the swap rate for U1 as shown on the following page. Again, we note that there is a maturity overlap and U1 falls between T4 and T5, which are maturity dates of the futures. From the futures quotes, we derived the corresponding zero coupon bond prices. So we are given the T4 bond and the T5 bond price. From these, we infer the T4 and the T5 simple spot rate, and then we use linear interpolation of these two simple spot rates to get the simple spot rate with maturity U1. The simple spot rate with maturity U1 gives us the U1 bond price, and then we can use the swap rate formula, which relates the swap rate for maturity U2 to the U1 and the U2 bond prices. We can solve this equation for the U2 bond price as shown here. For the remaining cash flow dates, we use linear interpolation to obtain the corresponding swap rates. We can then invert the swap rate formula to derive iteratively the UN bond price in terms of the previous bond prices and the corresponding swap rate, as shown here. We eventually obtain the UN bond prices for all the remaining maturities n from 3 to 30. Setting the initial value of the discount curve equal to 1, we thus have constructed the discount curve for 40 maturity time points, as shown here. Recall that the blue maturities S1, S2, S3 correspond to the LIBOR rates. The red maturities T1 up to T6 correspond to the futures rates, and the green maturities U1 up to U30 correspond to the swap rates. We also see again the overlap of these maturity spectrums. The T maturities overlap with the S maturities, and the green swap maturities overlap with the red T maturities. The figure on the left-hand side shows us the discount curve as a function of time to maturity. We see that the bulk of the maturity dates correspond to the swap contracts. If we zoom in to the first 3 years, this is what we see on the right-hand side, we see the short end of the discount curve. So here we can nicely distinguish between the LIBOR maturity dates, the futures reset and maturity dates, and then the first cash flow dates of the swap contracts. The figure on the left-hand side shows 3 curves. The first curve is the yield curve that corresponds to the discount curve. The second curve is the curve of simple spot rates. They look both decently smooth. But if we look at the forward curve, this is the middle curve here, we see some sawtooth. If we again zoom in into the first 3 years, this is what is shown on the right-hand side. We see the irregularities also showing up here. So in sum, the bootstrapping gives us an entire term structure from relatively few instruments. We had 3 LIBOR, 5 futures contracts, and 9 swap contracts. The method exactly reconstructs these market prices, and this is desirable for interest rate risk management and trading desks because they have to market their books. But the implied forward curve is irregular and sensitive to bond price variations. Bootstrapping is an example of an exact estimation method.